right, so here is part 2 of our balancing reactions. And we have one of, I love this reaction, I think it's fantastic. Aqueous hydrogen peroxide decomposes to produce oxygen and water. So, aqueous hydrogen peroxide decomposes. We'll talk about what this word means in a little bit, but to produce, so yields, sorry, not plus, oxygen and water. Again, we get to assume that since there were no conditions stated, that this is occurring at standard conditions, 22 to 25 degrees Celsius and 1 atmosphere of pressure. So, starting here, aqueous hydrogen peroxide. Hydrogen peroxide is kind of like water. You just need to no, it's not kind of like water. It is like water in the fact that you should just know the formula for it. You shouldn't have to sit there and try to figure out what the formula is. But it is not like water at all. Do not try to drink this stuff. Hydrogen peroxide, the formula for it is H2O2, and the statement told us that it was aqueous. Decomposes to produce oxygen, and oxygen is part of Brinkel-Hoff, so it is O2. And since we're at standard conditions, what's the state for oxygen? Well, thankfully, it's a gas. If it wasn't a gas, we'd have problems. And water. So water, of course, is H2O, and at standard conditions, that will be a liquid. And now it's time to balance. Well, what do you do when you only have hydrogen and oxygen? Well, pick one and start with it. I am going to start with the first one I get to. So I have 2 hydrogens here on the reactant side, and on the product side, you see that I have 2 hydrogens, so they are balanced. Now I'm going to go on to my oxygens. I have 2 oxygens here. I've got 2 here plus 1 here. So I have 2 oxygens on this side, and I have 3 oxygens on this side. Well, another trick that I can tell you, whenever you only have one source for an element and it is an even source, well, then you want to take whatever it is that's causing the amount to be odd on the other side and make it to where it's even. So I'm actually going to put a 2 here because I got 2 oxygens here and I got 1 oxygen here. And so the reason I'm going to do this is so that I now make it even, and I can find a least common multiple a lot more easily. So least common multiple between 2 and 4, well, I just need to multiply this guy by 2, and now I have 4 oxygens, and I have 2 plus 2, because remember this distributes through to everything that comes after it. So 2 plus 2 gives me 4 oxygens, so this guy's now 4. But you'll notice I just messed up my 2. So, but I just messed up my 2 over here. So maybe, luckily, hopefully, I messed them up in the same way. So I have 2 times 2 gives me 4 hydrogens. And over on this other side, I have 2 times 2 also gives me 4 hydrogens. So yay, happy accident. Next example. You have solid copper metal. You can see that right in here. Reacts with aqueous silver nitrate to produce solid silver metal, this kind of goopy stuff right here that's growing, that's pure silver, and aqueous copper 2 nitrate. You notice how as the reaction progresses, the liquid color gets more blue. Well, copper ions are blue, and so that's why silver ions are clear, copper ions are blue. So as the copper, the pure copper, starts to leave this little springy thing and go into solution, it causes the solution to turn blue. So this would be an example where a color change does indicate a chemical change. But it's not a color change by itself that does it. It's also the formation of a precipitate here, the formation of this solid. So, solid copper metal reacts with aqueous silver nitrate to produce solid silver and aqueous copper 2 nitrate. So I'm going to start with my solid copper. Well, the symbol for copper is Cu, and like we said, it's solid. reacts with aqueous silver nitrate. Well, the formula for silver nitrate, silver is always a +1 when it's in its ionic form, and nitrate is a polyatomic ion with a -1 charge, so these two guys just naturally go together. AgNO3 aqueous. To produce solid silver metal, so silver, and aqueous copper 2, which means we're dealing with the copper 2+, nitrate. Nitrate is still the same NO3 with a -1 charge. So bring these guys together, and you'll see when you do crisscross, you actually need 2 nitrates. So you're going to go Cu parentheses NO3 parentheses 2, and the question said that this was aqueous. Now again, if you don't remember how to write your formulas, go back and watch the Writing Chemical Formulas video to refresh your memory. So now I'm going to balance this guy. I'm going to start with my metals. So first metal I get to is copper. I have 1 copper on the reactant side, and I come over here and I have 1 copper on the product side, so yay. Moving on to silver, I have 1 silver on the reactant side, and I have 1 silver on the product side. So those are good. So all my metals are taken care of. Now I'm going to move on to polyatomic ions that went from one side of the reaction to the other without changing, and I just so happen to have one, my nitrate. So I have 1 nitrate over here. I have 2 nitrates on the product side. Now I can't just go, okay, well, let me just, how about I put some parentheses around this and plop a 2 outside of that? Well, no, I can't do that because that changed the formula. And we're not changing formulas here. The only thing that we can add is a coefficient. And now you're probably going, well, wait a minute, you just messed up my silver. Yeah, I did just mess up your silver. So we're going to have to go back and fix that. But now I have 2 nitrates and I have 2 nitrates. But like you noticed, I messed up my silvers, so now I have 2 silvers on the reactant side, so I need to have 2 silvers on the product side, and problem is solved. 1 or 2 more examples. Carbon dioxide gas is bubbled through water that contains solid barium carbonate, creating aqueous barium bicarbonate. This is kind of a complicated sounding reaction, but once we break it down, you'll see it's actually not that bad. So carbon dioxide gas is bubbled through. So basically is reacted with the water containing solid barium carbonate. Well, this is a little tricky here because you're going, oh, okay, it's bubbled through water. Well, no, that's not what it's actually mixing with. It's mixing with or reacting with solid barium carbonate. How did I know that? Well, I looked at the results. Creating aqueous, oh wait, that does mean our water's involved. Bam! So we got to add that into barium bicarbonate. So I got a bunch of things coming together. Oh, creating, that's where our arrow. So carbon dioxide gas, so that's CO2 gas, is bubbled through water containing solid barium carbonate. Well, to write your formula for barium, we know that barium is a +2, carbonate is a polyatomic ion CO3 with a -2 charge, and so that just naturally goes together, barium carbonate. And they did tell us that it was a solid, creating aqueous barium bicarbonate. Bicarbonate is sometimes called hydrogen carbonate. It's another polyatomic ion. Instead of the formula CO3 with a -2 charge, it has the formula H, CO3 with a -1 charge. So the formula for barium bicarbonate, we're going to need 1 barium and 2 bicarbonates to bond these guys together and balance out. So it's going to be Ba parentheses HCO3 parentheses 2, and this, like I said in the question, is aqueous. So now to balance it, start first with your metals. Well, what's your metal in this question? The metal in this question is barium. And look at your reactant side, and you'll see that you have 1 barium. And then look across to your product side, and you see that you also have 1 barium. So that one is balanced. Now, what I have left, I have carbon, polyatomic ions is what's next. So you see that I have a polyatomic ion here, CO3, and I have a polyatomic ion on the product side, HCO3. Because they're not the same, I can't balance them as a unit. I'm going to have to balance them as their individual elements. It's kind of a pain in the tuchus, but it is what it is. Okay, so what I have left, I have carbon, I have oxygen, I have hydrogen. I've already taken care of my barium, and then I got more carbon and more oxygen. Well, the amino says save oxygen and hydrogen for the very last, so I'm going to move on and do my carbon. So I got 1 carbon here, I got 2 carbons here. Well, 1 carbon for a total of 2, so 1 plus 1 is 2. Coming over here, remember this 2 goes to everything that's inside the parentheses. So I have 2 carbons. So 2 carbons on the reactant side, 2 carbons on the product side. So those guys are good. Then oxygen or hydrogen next. Again, it doesn't really matter which one you do. So I'm just going to pick the first one that I get to. So you can see here that I have 2 oxygens plus 1 oxygen gives me 3 plus 3 more gives me a total of 6 oxygens on the reactant side. And I'm going to come over to the product side. Well, I got 2 times 3. That's 6 oxygens. Hey, there we go. Then the last element that I need to balance is my hydrogens. And you'll see that I have 2 hydrogens here. And coming over to the product side, I have 2 times our little imaginary 1 there. Hydrogen, so 2 hydrogens on this side. So this one was another one that was naturally balanced. Gotta love those. The last example problem that I have, sorry I didn't have a picture for that one, by the way. Acetic acid solution is added to a solution of magnesium bicarbonate to create water, carbon dioxide gas, and aqueous magnesium acetate. So my chemicals are acetic acid, and solution is another word for saying aqueous, is added to a solution of magnesium bicarbonate, there's that bicarbonate again, to create water, carbon dioxide gas, and so water, comma, is a plus sign. The word and is also a plus sign. Aqueous magnesium acetate. So the first thing to do is write the formula for acetic acid. Well, you have to know your acetate polyatomic ion, and if you look that up, you'll see that it is CH3COOH, aqueous. You can also write this as C2H3O2H. That is acceptable. C2H4O2, not so much, because you need to show that this hydrogen is not a part of the acetate ion. It's it's bonded to it, but it's separate from the acetate polyatomic ion. So if you did C2H4O2, then I would not be okay with that. I like writing it like this because this shows structure, and I am an organic chemistry nut, so welcome. Is added to a solution of magnesium bicarbonate. Well, magnesium is in group 2, so it has a 2+ charge. And bicarbonate, same polyatomic ion we used on the last one, HCO3 with a -1 charge. So we're going to need 1 magnesium and 2 bicarbonates. So Mg parentheses HCO3 parentheses 2. And it is a solution of, so that's going to be aqueous, to create water, which is going to be a liquid, carbon dioxide gas, so CO2 gas, and aqueous magnesium acetate. I'm going to write that down here because I'm kind of running out of room. So magnesium is still a +2. This right here, C2H3O2, or you can write CH3COO, that is the acetate ion, and it actually has a -1 charge. So I'm going to write it like that. Magnesium, and magnesium's a +2, acetate's a -1, so I'm going to need 2 CH3COOs. And like the question said, That is aqueous. So now balancing this, we're going to start with our metals. Well, the only metal we have is magnesium. And we have 1 magnesium on the reactants. We have 1 magnesium on the products, so they are balanced. Then what I have left is carbon, hydrogen, and oxygen. And you'll notice I've got them in a couple of different places. And so you'll have to kind of, ooh, wait a minute. We have acetate on both sides. We have a CH3COO on both sides. So I'm going to balance those guys as polyatomic ions. So I have 1 CH3COO on the reactant side, and I have 2 CH3COOs on the product side. So I'm going to put a 2 out front of my acetic acid. And now I no longer have to deal with what is in these boxes. And I can move on to my nonmetals that do not include carbon do not include oxygen or hydrogen, and carbon is the only guy I got left. So I got 2 carbons on the reactant side, and looking over here, I got none there, I got 1 there. These carbons, I'm not going to count those because they're a part of my acetate ion, and I've already taken care of them. So I have 2 carbons here. I only have 1 right here, so I'm going to put a 2 out front of my CO2. Now moving on to, let's see, hydrogens is what I come to first. So I have 2 hydrogens here, and again, I'm not counting these hydrogens because they're a part of the acetate ion. So I'm only counting things that are not a part of that polyatomic ion that I've already balanced. So I've got 2 hydrogens here. I have 2 hydrogens here for a grand total of 4. Coming over to the other side, I've got 2 hydrogens and nothing else. Again, not counting this hydrogen because it is part of the acetate ion that I have already balanced. So since I have 2 hydrogens on the product side and I need to have 4, I'm going to put a 2 in front of my water. So now I have 2 times 2 or 4 hydrogens. And the last thing that I need to balance is the oxygens. And again, not going to worry about these oxygens in here because they have already been taken care of as a part of the acetate ion. So the only oxygens I need to worry about are these guys right here. Well, I've got 2 O3s. So 2 times 3 gives me 6. And coming over here, I have 2 oxygens right here. And I have 2 times 2 gives me a total of 4 oxygen, so 2 plus 4 gives me 6, and so my oxygens are balanced. And that, ladies and gents, is all I have for balancing reactions, and I will see y'all later.